Bismillahirrahmanirrahim. So, in lecture number 16 today, we would like to come up with a derivation for the phononic model of crystal oscillations. We've already seen that the oscillations inside a crystal can be represented by these coordinated movements between atoms, which were called phonons, and these phonons are quasi-particles. So instead of looking at crystal oscillations from a mechanical perspective, it's equivalent to look at all of these oscillations in a gaseous model, in which you have a gas of non-interacting particles called phonons. So all the oscillations inside the atom, which is by far a very complex undertaking, is reproduced to a gas of phonons, and these phonons do not interact with one another in the harmonic approximation. And we came up with expressions such as the expression for the total energy in this gas of phonons, which is given by an integral over frequency, where the frequency of each phonon is given by h bar omega, and we look at the number of phonons in each mode, which is defined by omega and k. So we have E just bar h bar omega over kBt minus 1, and then we multiply this with the density of states, g omega. So this gave us an expression for the total energy contained inside a gas of phonons. So now the entire solid, which is a collection of atoms and they're oscillating, is reduced to these quasi-particles, phonons, which in a cartoonic representation are moving just like a gas inside a container. Okay, and they are non-interacting with one another, at least in the harmonic approximation. So today we are going to derive an expression for the Hamiltonian for these quantized oscillations, and we would like to see that in the harmonic approximation the Hamiltonian is indeed given by this form h bar omega, the operator corresponding to the number of phonons, which is a dagger a plus half. So we'd like to see whether the oscillations that we've derived, starting from a purely Newtonian classical picture, if that energy can be quantized to yield a Hamiltonian of this form. So if we would like to sum up the title of today's lecture, we would like to say that phonons exist. Okay, so this is a slightly witty title, but phonons exist really means that we can come up with a model in which we can treat these oscillations as quasi-particles. And if we look at, by the way, the energy level description, we have these equally spaced levels, energy levels, and being in a particular level really means that we have excited that number of phonons. So if this is level number 1, 2, 3, 4, 5, 6, this means that we have 6 phonons in the system, 6 particles in the system, each with energy h bar omega. And of course there has to be some ground state energy as well. So having more phonons, having more particles called phonons, is like having a higher number of excitations in the system. Okay, physically this would correspond to a bigger amplitude. But remember, we never make the amplitude so big that this potential energy curve departs from its parabolic shape. So we always remain inside the harmonic approximation. So let's derive this Hamiltonian. Once we have this Hamiltonian, we know what its eigenstates are. These are just the number states telling us the number of phonons in the system and so on. So we'll start off again with the classical model. We do know that classically there is some kinetic energy, there is some potential energy. And we've also come up with an ansatz for an oscillation for an atom in unit cell n, ath atom, and along the I direction. And this ansatz was equal to some amplitude uai. This is independent of n because of translational invariance, because each unit cell is just the same, so it should not depend upon n, this amplitude. And then we have some phase eik dotted with Rn, where Rn is the location of the nth unit cell, E minus I omega t, and we also normalize this with the mass of the atom, with a square root sign. So this was our starting point when we derived the dispersion relationship for the phonons. Okay, and then finding the equation of motion reduced to finding a dynamical equation for the UAIs. Correct? So if this were a solution, then we would also know that if we create arbitrary superpositions of this, that will also be a superposition, that will also be a solution of the equation of motion. Correct? So if this is a solution, then this would also be a solution if I multiply each of the solution with an amplitude q, which could be a function of k. Let's multiply this with, let's call this f, some function of k, okay, and sum over all k's. This would also be a solution, correct? A linear superposition of solution is also a solution of an equation of motion. And by the way, this amplitude can depend upon k. So now this is starting looking like a Fourier transform because of this exponential term. Now there's a time dependent term here. If I just lump that time independent term into f, so if I say that my f k e minus I omega t is some q k t, so that's okay to do. So my s n a I, which is my amplitude of oscillation, how far am I from the equilibrium position? Each atom in the nth unit cell, ath atom, is away from its equilibrium position along the I direction, is going to be given by sum over k's 1 over m q k t e I k r n u a I k. All right. Now we do also know that there could be different branches inside the dispersion relationship. So corresponding to 1 k, this is k, this is omega, there could be multiple branches. So each branch can be indexed by this number r. Right? So we really have to take the sum over all r's as well. So this total amplitude of oscillation at a given k, at some k here, can lead to an omega at k either here or here. So this can be characterized by an omega r. So each of these modes, so there's a mode here and a mode here. So you need to sum up over all the modes, which really means that you need to sum up over r's, with this q is indexed by r. Now don't confuse this r with this notation rn. R on its own without a subscript just represents the branch, and this amplitude needs to also to be indexed, demarcated with respect to the r. So this is a sum over all modes. So you sum up over all k's, all possible k's and all possible r's to find out the total amplitude in the direct space. Okay, this by the way is a Fourier coefficient because it's indexed not with respect to position but with respect to k. So this is our S. This is our amplitude, all from mechanics. Now we would like to find out the total kinetic energy of this system. Okay, so what we're trying to do is we're looking at the amplitudes of oscillations, and from that we want to find out the total kinetic energy, the total potential energy, then we find the Lagrangian, then we find the Hamiltonian and see if it matches with this. That's what we would like to do. So now we know that the total kinetic energy for this system is going to be equal to half. All the atoms say have the same mass m and the velocity squared. So we really need to take the velocity SNAI. This is the velocity. You take the time derivative and then you square this and sum up over all n, all a, all I. This will give us the total energy inside the system for all the modes. Now we want to express this in the Fourier domain in the k space, and we already have an expression for this. So we need to take, if you look at the dot product, the time derivative, the only time dependent term is this term. So you put a dot over here to find the velocity, and then you take the square of this. So now there is already a sigma in it. So now you have a sum of dots, and then you take a square of it. So you get a product of two sums. Okay? And in order to do this properly, we would have to write this in the following fashion: 1/2 m NAI square of this. So this 1 over under root m becomes m. So once you have sum over k r q r k comma t e I k r n u a I k r. But since you have a sum over k over r, once you multiply this with another sum of k over r, you have to change the indexes for k and r. Right? So you will then have another sum. Since you have this square over here, you have another sum in which you use different indices k and r. So you use k prime, r prime. But you still use the same Rn, same AI. Okay? So this becomes q r prime k prime t e I k prime r n u a I k prime r prime, and this is sum over k prime r prime, right? Because these indices n, a and I don't change because you take the dot product and square, so you're still looking at the sum over n a I. So that's why this n doesn't change across these sums, this a I doesn't change. But since you have a summation over k and r, these variables do change. That's the proper way of doing a square. So this becomes half, sorry, it's a dot here. So this becomes NAI K prime R prime QR K. So I'm just suppressing this time dependence here for the time being, okay? I just assume it's there. QR dot, QR prime, K prime dot. This becomes EIK plus K prime RN. This becomes UAI K R UAI K prime R prime. Now if you look at this sum, the only term that has an n in it is this term. So I can just take this summation over n and put this sigma over n over here, correct? Now this is a sum in which the exponent is rapidly varying because this k and k prime are spanning the entire first Brillouin zone. So this sum is always 0 unless k plus k prime is a multiple of the reciprocal lattice vector. So if this is some product of some factor of g times r, and this will become ei 2 pi with some integer, so this will become 1. So this term is 0 unless k plus k prime equals some reciprocal lattice vector. So in other words, this sum is equal to, is non-zero only when k plus k prime is some reciprocal lattice vector g. Okay, and for normalization we also have n. So this kind of sum over k space, discrete sum over k space equals to the Kronecker delta is very common in quantum field theory. It's used whenever you have a quantized system. Okay, it's very common. Sum over n gives you a Kronecker delta in which this exponent has to be equal to 0, and that is equal to 0 when k plus k prime is some reciprocal lattice vector. Now since all of these k's are in the first Brillouin zone, therefore in the first Brillouin zone you do not go outside the first Brillouin zone, so the reciprocal lattice vector which connects points inside the first Brillouin zone is 0, because when g equals 1g you go outside the first Brillouin zone, when g equals 2g you go into another Brillouin zone. If I look at this in 2 dimensions, this is my first Brillouin zone, this is my gamma point, this is pi by a here, this is also pi by a. So this really means that if I have a vector k, then k plus k prime it must equal to reciprocal lattice vector, but the reciprocal lattice vector can, if I have anything beyond 0, so if I have g, this will go outside the first Brillouin zone. So this really has to be inside the first Brillouin, and the only way in which this can happen is that g equals 0, which means that k prime plus k equals 0, which means k prime is equal to minus k, which means that k prime is opposite of k. So this is really saying that n, this Kronecker delta is k prime equals minus k. So when I insert this Kronecker delta function into here, all the k primes are replaced by minus k, correct? So this becomes, this kinetic energy becomes half ai r prime, and just k, because I'm going to suppress all the k primes. This is qr dot k. This is qr prime minus k dot this n kind of there was an n somewhere. Oh, here when I do this substitution, it's conventionally to put a square root n here as well. When I do this substitution, when I take the sum, I need to normalize, so I divide by 1 over under root n as well. So there's an under root n over here. Root n, under root n, but this would cancel this out. So this is under root n here. Let me see. When I take the square, this goes away. Okay. So there's an under root n here. When I take the square, this square root goes away. Finally, the n just vanishes from this kinetic energy expression. So this becomes uai k with an r. This becomes uai r prime minus k. Okay, so this is my kinetic energy. All right, so now something very interesting. So let's call this equation number 1. Let's call this equation number 2. So now I would like to look at some interesting properties and simplify this a bit further. So one thing you observe from number 1 is that S, the amplitude, is real. It's a mechanical amplitude, it's real. But the right hand side looks like complex. So if I take the complex conjugate of equation number 1, SNAI complex conjugate, this would give me 1 over square root nm k r q r star complex conjugate kt u a I r star k e plus I k dotted with r n, right? This is the complex conjugate of equation number 1. Okay, but if this complex conjugate must equal the amplitude itself because S is real. So there was this will be minus, yes. This would be minus, right? So if this is real, then this must be true. Now this can only be true, this can only be equal to equation number 1 if the only way possible is that this term, so these two terms must be equal, 1 over n k r q r kt u a I r star without the star, sorry, e plus I k dot n. So this must be true, correct? Now when are these two expressions just the same? So if this is a sum over all k's, now this case includes positive and negative k's. So it will not make a difference if I, in this second equation that I've written, replace k by minus k, because it's a sum over all k's, minus and positive. So I'm spanning this entire first Brillouin zone, so I'm taking into account positive k's as well as minus k's. So the sum over k is the same as the sum over minus k. So what I could do is I could replace this k with a minus sign without making any difference. So this become a minus sign, minus here, minus, right? Now if I compare these expressions, this means that this term must equal this term, and these amplitudes must be equal. So this means that if I take q for some r and I take the complex conjugate of this function, this will be the same as qr minus kt, and u kt for any ai must be the same as uai, the complex conjugate of this with, right? Okay, so this is true if S is real. So whenever the Fourier transform is real, the Fourier coefficients, if you compose them inside a matrix, they will form a Hermitian matrix. This is a property of Fourier transforms. So now when we have this relationship over here, this term over here, and this term over here can be replaced by their complex conjugates. So in equation number 2, my total kinetic energy would be expressed as half k r, and I'll take into account the ai term later in a minute, q r k q r prime k complex with dots, right? Correct? Uai k r uai k r prime, but with complex conjugate. Now I'm taking this summation a over ai, I'm writing this next to these u's, because it is only that these terms have an ai in them. Now if my dynamical matrix is symmetric, which it is, and this is a homework problem, if the dynamical matrix is symmetric, these u's are orthogonal. So all of these u's form a vector, and for a symmetric matrix we know that the eigenvectors can always be made to be orthogonal to one another. This comes from linear algebra. So this sum is 1 if r and r prime are the same, because it's sum over all ai's. So I'm looking at all the eigenvectors of a dynamical matrix which is symmetric, and I'm putting them all together, and they form an orthogonal set. So this term will be equal to 1 if r equals r dot r prime. So this equals really Kronecker delta r prime, because of the orthogonality of these vectors. Now when this is true, I can replace this r prime with r, and this, so this was previously sum over r and r prime, Now I will just be left with half k r q r dot k q r k dot complex conjugate. So this is my kinetic energy. Right? So we've solved the kinetic energy part. So remember that for a harmonic oscillator, the one that we've drawn over there, the energy is half mv square plus half kx square if you look at a one-dimensional problem. So it's half of the square of a coordinate. So if I look at my 1D harmonic oscillator, I do know that my energy is half m x dot squared plus half k or omega over m or something of that, omega square over m x squared, right? So look at the form for this energy. The kinetic energy is the square of the dot of a coordinate. So this is my position coordinate, x dot is the momentum coordinate, and position and momentum are conjugate variables, and it's always the square of these normal coordinates. So position and momentum are the normal coordinates. This kinetic energy has a similar form. Q dot is, as I will show in a minute, is a momentum associated with a normal coordinate q. So this term is the same as this term. It has the same form as this term. Now we would like to look at the potential energy term for our harmonic oscillator. Right, so we solve the kinetic energy part. Let's call this equation number 3. Now the nice thing for the kinetic energy is that this is a one body Hamiltonian. You see, this is only one body at a time, Na ith body. So it's a one body Hamiltonian. But the potential energy is an interaction between two atoms. Remember the phi that we talked about, the spring constant. It connects two position coordinates. So that's a two body Hamiltonian that we want to solve now. So let's now try to find out the potential energy for this system. So the potential energy for this system is, as we all know, is of the kind of half kx square. It's given by so we have some interaction between the atoms. So the strength of that interaction is given by a phi, the spring constant. And we know that this spring constant connects two atoms, NaI, M, Bj. And we've already looked at properties of this interaction. It does not depend upon n. It only depends upon m minus n. It does not depend upon which unit cell you're talking about. It only depends upon the interaction across different unit cells and across different atoms inside the unit cell. So this phi, this is a phi, it has certain properties. We know that this is also the second order derivative of the energy. And then I have an amplitude SNAI and an amplitude SMBJ. Right? So this is like a half kx squared. This is the displacement from equilibrium of one atom, and this is the displacement from equilibrium of another atom, between which we are looking at the interactions, and the interaction strength is captured inside this phi. We've already seen this. So we need to sum over NaI MBJ. But since this is a pairwise interaction, so when you take two atoms and then you run the variables, you are counting each interaction twice. So you need to divide this by 1/2. So this is the potential energy. So now what we could do, we've already expressed these S's in terms of the normal variables Q here, like this. So now let's try to write down these S's in terms of the normal variables. So I'm left with half. So m will be squared half m N, NAI, MBJ, once again, I will have to choose two kinds of variables, K and K prime, R and R prime, right? Because I have a product. So I'm left with QR KT, QR prime K prime T. I have a phi. Now phi NAI, let me, okay, for the time let's try this. NAI MBJ. I have U AI function of K, or UBJ K prime R prime. Anything else that I've forgotten? Yes. E I K R N E I K prime R N. Okay. So this is our potential energy term so far. Okay. So now let's kind of look at these exponents. So I'm just going to focus on these product of exponents for a minute. So EI K R N and EI K prime R N. So let me write this as EI K. Just a minute. The slight trick I would like to use here. EIKRN, ठीक है. EIKRN. I insert minus I KRM on my own, right? And then I have to do the inverse plus IKRM. Okay. So I have resolved identity into these two terms. I'm left with E I K prime R N. And then what I would like to do, I would so I write this as E I K R N minus R M E I M है एक मिनट this is R N minus R M, this is second R N minus R M R M E I K prime R N E I K R M E I K prime R N. Okay, let's see what happens. Okay, so E I K minus sign R M minus R N E I K R M E I K prime R N. Okay.
That needs to be R M and the last one.
This one? Yeah, you're right, probably. Yes. Just a minute. Sorry, yes. Sorry, this is RM. Thank you. This is, thank you. RM. Right? So this becomes E minus Ik. Now Rm minus Rn. So there are two unit cells. Say this is Rn. This is the next unit cell Rm. Let me call Rm minus Rn this vector, which is a translation between two unit cells. Let's call this vector D. Okay. So this will become E minus I k dot with D. E I k plus k prime with Rm. Correct? All right. So now if I now consider this term together with these exponents and look at some of these sums, let's see what we get. Okay? So phi NAI MBJ and these two exponents EIKRN EIK prime RM. This equals, now I can put this n equal to 0. This m will then be replaced by m minus n because of translation invariance, because we have a lattice. So this becomes phi. 0 is just a constant, some fixed reference point. AI m minus n. I call that D. BJ, right? Now this entire exponent has become E minus I k dot with D. E I k plus k prime Rm. So this is sum over, I'm just looking at the sum over m and n. So I'm just trying to kind of resolve these sums. And m and n are nowhere else in any other variable, so I can do that. So there's no m or n here, none of them is here. So I can take that sum over m or n separately. So this, but this I can replace by a sum over, I have now two variables m and d. I can replace this by m and d, right? Good. Now there is no m over here. There's a d here, but there's an m over here, right? So I can take this sum over m here. Correct? Now this sum over n, this thing, once again using our Einstein's summation rule, this sum over discrete points is again equal to the number of points n Kronecker delta k prime minus k. Fine? So far so good. So what I could do next, I could now express my potential energy as half, this n just goes away and I'm left with half m one over 2 m sum over ai, sum over bj, sum over k, sum over r and r prime. Still we have the R and R primes with us. QR KT, QR prime, K prime is now minus K T, and sum over D phi 0 AI D Bj, okay, U Bj. So first of all I'm going to write this term here, U Bj, K prime is minus K, this is an R prime, and I have UAI K is an R. So far so good.
Exponential term. Exponential iota k t.
And all right, so now any other guesses? If I look at this phi, this is an interaction, this is the EIK, and the distance between from and the same distance d, m minus n, appears here. This thing into this thing divided by 1 over m square root into 1 over m square 1 over m. This is just the dynamical matrix element. So I would like to write this down. This sum over D phi 0 AI D Bj U Bj minus K R prime E minus I K prime D 1 over m, right? So I've taken this m, I've taken this and this and this, right? I'm writing it separately. Now I do know that this, if I replace this minus k with a plus k and put complex conjugate here, it doesn't matter. Correct? And I do know that so let's do that at the end. Let's do that at the end. I do know that this term over here equals a dynamical matrix element D, which is indexed by AI and Bj independent of n from its very definition, minus k, right? We do know this. Good. But we do know that the dynamical matrix element is a Hermitian matrix because of the presence of these pairwise interactions. So this equals DAI Bj K. In other words, and we also know that if I replace minus k with plus k in a symmetric matrix element, since there's a property of dispersion relationships that it is an it's an even function of k. If I replace this minus k with a plus k, it doesn't change. This matrix element doesn't change. So now all of this so this is, so one thing, sorry, I made one mistake over here. Right, so I need to put this thing in here as well. So this sum over D only, I can put this like this, right? This sum over D, U, Bj minus K, which I now make this K star, okay? I replace this with K star, with an R prime, okay? So this is true, correct? Isn't it? So what I've done is, I've taken this thing and this thing and it's summed over the distances, and this thing, this equals this without the sum over D. That's the definition of the dynamical matrix. Now this entire sum has been replaced by a matrix element. This is a matrix element. This matrix element acts on this. Correct? So now what I've done, I have taken care of this sum over D. I do also have a sum over Bj's. So let's take this to the next step. My V becomes 1/2 sum over AI, sum over Bj, sum over K, sum over R and R prime, QR KT, QR prime minus K T. What next? DAI Bj minus K, I can replace simply with K because the dynamical matrix element is symmetric. U Bj over K R prime complex conjugate. And I also have UAI K R. Okay? So what I could do next, I could take this sum over Bj, I can bring this sum over here, because that's the only location where I have a Bj. I do therefore know that the sum of DAI Bj at K acting on UBj K R prime, by the very definition of the dynamical matrix element and the equation of motion, this equals omega square UAI K R prime, right? That's the definition of the dynamical matrix element. This is the equation of motion written in another way. Therefore, if I have a complex conjugate over here, as I have here, I will get a complex conjugate over here. That's the only thing that's going to happen. Okay? So far so good. This matrix, I can take a complex conjugate here as well, but this is a Hermitian matrix anyway. Therefore, I can replace this entire thing and this sum over Bj by UAI R prime complex conjugate. So my potential energy now takes this very nice form. V becomes equal to 1/2 AI K R R prime QR KT QR prime minus K T omega square. So let's put an omega square over here. This omega, by the way, is dependent upon K. So this omega is a function of K and R. So let's put this inside here, omega square, okay? And then I have U AI K R and UAI K R prime starred. Now I take this sum over AI. This sum over AI I can take here. And this will once again give me the Kronecker delta R prime because of the orthogonality. So my V becomes equal to half K sum over R omega square QR KT. Now this QR prime has to be replaced by QR. This I can just invert the sign of K and put a complex conjugate over here. QR star KT. This is my potential energy. So now I have found out a very nice form for the kinetic energy and an equally pleasing and satisfying form for the potential energy. This is my equation number 4. And both of them seem to be the square of some normal coordinates. So this is the square of Q, which is like a position coordinate. This kinetic energy has the time derivative of those position coordinates. So Q dot is like a momentum coordinate. Correct? So my potential energy, or sorry, let's now compose a Lagrangian because we would like to find out the Hamiltonian. Let's first of all write down the Lagrangian for this system. The Lagrangian we all know is the difference between the kinetic and the potential energy terms. So I'm left with half sum over K sum over R. So notice one thing, I've changed the coordinates. I've moved to the normal coordinates, which are expressed in terms of the Fourier coefficients, in terms of the K vectors. We are now in the reciprocal space. Okay. So now my Lagrangian would be that kinetic energy term QR KT, QR, sorry, with a dot, QR dot, KT star plus omega square QR KT QR KT star, right? So this is my Lagrangian. Now from the Lagrangian, if I have one normal coordinate Q, I want to find the conjugate momentum. I take the derivative of the Lagrangian with respect to the time derivative of Q. I get the conjugate momentum. And you can, if you kind of remember, forget all of this, take half mx dot square minus half kx square, take the derivative. So let me give you an example. Let me give you an example so that you refresh your memory about Lagrangians. So for a 1D harmonic oscillator, our Lagrangian is half mx dot square minus half kx square, right? If I take this Lagrangian and take the derivative with respect to the time derivative of, so x is my normal coordinate position, take the time derivative of this and find the derivative of L with respect to the time derivative, I'll find the momentum P for this system, the momentum that is conjugate to x. Let's see what I get. So now I treat x and x dot as two independent variables. So the time derivative of with respect of this with respect to x dot is 0, of this is 2 x dot, and I'm left with mx dot. This is the momentum that is conjugate to x. And then you all know that if you want to quantize this harmonic oscillator, you define x and p to be operators, and then you get iota h bar. If this is true, then you have quantized your system. So now we would like to do exactly the same thing over here. We have the Lagrangian and we would like to find the derivative of the Lagrangian with respect to q r kt naught, right? So the second term does not have a q dot, so its derivative is 0. In the first term, I will treat q dot and q dot star as two independent variables. So when I take the derivative with respect to q dot, I will be left with q r star dot kt, right? So if I take the derivative of this is treated as a constant. I'm taking the derivative of this, I will be left with this term. Now you may be wondering, what about the 1/2? So what about the 1/2? So remember that this is a modulus squared. So what I could do is I could do a trick, or just to understand, what I could write is that my suppose my QR, so I'm now not writing the QRK again and again. So my Q is, suppose Q plus Q1 plus IQ2. My Q star will be Q1 minus IQ2, right? And I have Q star. I'll talk about the 1/2 in a minute. Q star is simply Q1 square plus Q2 square, correct? Now if I take the derivative with respect to, first of all let's take the derivative with respect to Q1, I will get P1, right, which, sorry, with respect to, so now I want to put a Q dot here, okay, Q dot. Because I'm dealing with dots. This will give me P1, correct? Which is the real part of the conjugate momentum, which is the momentum associated with Q1, the momentum that is conjugate to Q1, correct? So now what is this equal to? So I take this and I take the derivative with respect to Q1 dot, I will get 2 Q1. Likewise, the derivative of Q dot, Q star dot with respect to Q2 dot will give me P2. This will be 2 Q2, right? So which means that this term over here is capital Q dot star with the 1/2. So I'm now kind of taking the derivative of the Lagrangian. So when I take the derivative of 2Q1, sorry. Right. So now what I need to do, I need to take the derivative of Q dot, Q star dot 1/2 with respect to Q dot, capital Q dot. Of course, I'll get this 1/2 plus into this momentum P1, small p2 with an iota sign. Because now the momentum has a real part and an imaginary part. So I get a momentum real part and a momentum the imaginary part with an iota. And This will be one, there will be 1/2 here as well. And this will give me the overall momentum dot R kt, correct? Because I do know that if I take for the Lagrangian, I need to put into this half, I take the derivative with respect to q dot, I will get a real part of the momentum and an imaginary part of the momentum, and this will be equal, must equal this, correct? So now P1, so this thing PR dot Q2 is simply equal to 2Q1 dot 2Q1 dot small q1 dot 2Q2 dot divided by 2, which is Q1 dot plus Q2 dot. Sorry. Plus there's an iota here as well, iota. Right? Which is simply Q dot so this is Q dot. This equals PR kt, right? So that's what we've seen. So this PR, this is PR, sorry, this is PR. ये PR है, ठीक है? So this PR is equal to Q dot. PR equals Q dot. So let me reiterate. I have a Lagrangian. The kinetic energy term has Q, which is complex, and a dot on it, and its complex conjugate. So I break this Q into the real and imaginary parts, small q1 and small q2. This is how I break this up. Now in the numerator I have this product, so this is equal to this. Now how do I find out the conjugate momentums? So there is one position coordinate small q1, one position coordinate small q2. I find the conjugate momentum to q1, which turns out to be 2q1 dot. The momentum conjugate to q2, this turns out to 2q2 dot. So the overall momentum, which will now have a real and imaginary part, will be this thing plus iota times this thing. And I need to divide by 2 because I need to take into account the entire Lagrangian. So overall I'll be left with this and this. But this thing must equal the momentum conjugate to q. So this means that the conjugate momentum P is given by this. So now the Lagrangian can be written in terms of the momentums and the coordinates, normal coordinates. I will be left with 1/2 sum over k, sum over r. Now each of the q dot is to be replaced by a PR. So I'm left PR dot, QR dot is replaced by PR kt, and q dot star is replaced with PR kt complex conjugate plus omega square QR kt QR star kt. So now I've expressed this Lagrangian minus sign, sorry. I've expressed this Lagrangian in terms of position and momentum. Right? So once I have the Lagrangian, I can find out the Hamiltonian. Right? So how do I find out the Hamiltonian? The Hamiltonian is PQ dot minus the Lagrangian. So from classical mechanics, given the Lagrangian, I know that the Hamiltonian is going to be equal to P R kt Q R kt minus the Lagrangian, right? Sum over k's and sum over r's. This is from something we know from classical mechanics. Right? So now I express this L in terms, I substitute this into my expression for the Hamiltonian, which I call equation number something, equation number, I don't know, let's call this equation number 4 perhaps. Okay, so my Hamiltonian now turns out to be equal to kr pq dot. So pr kt q dot qr dot so this is qr dot is pr qr dot is this another pr just a minute, so this is dot is complex conjugate over here. So qr dot. So if I'm dealing with complex, okay. Sorry, if I'm dealing with complex, so the definition puts a star over here. So if I'm dealing with complex numbers, so this is how we define the Hamiltonian, PR into QR dot star. If you're dealing with complex numbers, so we have PR KT, PR star KT. This is Q dot, Q star dot minus half PR KT, PR star KT minus omega square QR KT, QR star KT. So this will give us KR PR KT, PR star KT plus omega square QR KT, QR star KT. Okay, 1/2. Correct? This is my Hamiltonian. Now I need to quantize this. So if I treat these functions, could be complex functions, as quantum operators, I can put hats over here. Put a hat over here. So this is my equation number 6 and my Hamiltonian. Equation number 5 and my Hamiltonian, provided I have this relationship QR KT commutator with PR KT when these R's are the same. This must equal iota h bar. Correct? Provided this is true, then I can treat P and Q's as quantum operators and the Hamiltonian becomes a quantum operator. This has to be true. Okay. Now what I would like to do, I would like to express this in terms of some coordinate transformation which would yield a quadratic form. It's not a truly quadratic form at the moment. This part in itself is quadratic, this part in itself is quadratic, but when you take the sum, it's no longer quadratic. So you have to create some superposition of the P operator and the Q operator, the position operator and the momentum operator, and you have to do that transformation which would create something which is purely quadratic. Now what we could do for that purpose, any questions about this? I think this is a neat, clear derivation for the Hamiltonian. We just need to look at the final step. Remember that the commutator of QR with another position coordinate operator is 0, and so on for the P's. Now what we could do is we could define ladder operators A, which of course depends upon K and R, right? Some R, but I'm not going to write this R over and over again. I'm assuming that this is a sum over all R's, and all of this is dependent upon R. Okay? So I need to define an annihilation operator and a creation operator. I need to do this, right? So I could use 1 over 2h bar omega. Remember now this omega is a function of k, the same k. But omega, remember, is a real function of k. So omega minus k is the same as omega k. So, right? And I make this definition, this substitution, a canonical transformation, omega QR, of course this depends upon k and t, plus iota PR star. And remember the properties of complex conjugates. So the complex conjugate is the same as replacing k with minus k. So with this definition and the definition 1 over 2h bar omega omega QR star minus IPR. So now I can invert these relationships and express Q and P in terms of A and A dagger. So when I do this and I place all of this in here, and keep in mind, finally I keep in mind the fact that P of R KT, if I take the complex conjugate of this equals PR minus KT. So it's the same as PR replacing K with minus K. So keeping this thing in mind. So if I invert these expressions, let me write down the final result. My Q R KT equals h bar over 2 omega square root A K plus A dagger minus K and PR KT equals 1 over iota h bar omega over 2 A K minus A dagger minus K. And remember, these A's are also indexed by R, but I don't want to write them over and over again. So if I do this inverse transformation, this is how K is represented in terms of the ladder operators and how P is represented in terms of ladder operators. Remember one thing, if I take the complex conjugate of this function, I do not change the sign of this iota. What I could do, without changing the sign of this iota, I could replace these K's with minus K's by the very definition of the fact that the amplitudes are real. Okay, so with this form, I can rewrite my Hamiltonian. And at the last stage, what I would achieve is the following. Any guesses? I also need to keep in mind that my sum over K's is the same as my sum over minus K's, because I'm in the first Boolean zone. So there's one additional trick that you would need to remember. Okay, so when I put these coordinate transformations into the Hamiltonian and I replace these normal coordinates and their conjugate momenta by the ladder operators, the final Hamiltonian that I receive is going to be H bar is H bar omega. Now I'm going to write the full form, A R dagger K A R plus half. Okay, sum over, since I have to do the summation over all modes that exist inside the system, and there could be 3 times R times n modes inside the system. It's a 3-dimensional system we're talking about. I need to take the sum over all K's, which is the entire countable number of states that exist inside the first Boolean zone, and the sum over all branches R. That depends upon the size of the motif, size of the basis that goes at each lattice point. So this is the overall Hamiltonian. Okay, so this reproduces the quantum harmonic oscillator. So now these phonons can be expressed by their Hamiltonian. Their energies will be the eigenstates of this Hamiltonian, given by H bar omega R K. So I index these K's with the Kn and R half plus the number of phonons inside this mode. This is the energy for the gas of phonons. And from this we can derive all quantities related to the energy. Number statistics, the number of phonons inside the system at a given temperature, and so on. From the energy, we can calculate, of course, the heat capacities. We can also calculate mechanical properties, stiffness constants, and so on. The Grunzian ratio and the bulk modulus as well. So all of this is stemming out from here. So now, even though in the previous lectures we have kind of focused on utilizing this idea of phonons for different calculations, now I've given you an explicit derivation of how this Hamiltonian can be derived, which gives us the confidence that the phonons, non-interacting phonons, these phonons do not interact with one another. All of them are independent. They are uncoupled. This uncoupled gas of phonons, which do not collide with one another, do not interact with one another, they act like independent particles. So this idea of treating an oscillation with particles is an example of second quantization. First quantization treats quantum systems like waves. The second quantization treats them like particles. So now we have these particles called phonons inside the system. Okay, so we'll have our midterm day after tomorrow, inshallah.